Our next section is going to be on orbits. So imagine, if you will, a giant cannon on top of the Earth, and we're going to fire out a cannonball. If there were no gravity and we fired our cannonball, it would simply travel off in a straight line forever until a force touched it. Well, that doesn't happen. We do have gravity, so when we fire our cannonball, it goes and it simply falls to the Earth. If we were to fire it with more power, it's still going to have a trajectory, but it might go a little bit farther, so it's going to have a little bit more of a range. Well, let's keep increasing our firepower. So it falls and it falls and it falls and it falls, and gravity pulls it down. Well, if I'm able to have a huge explosion and fire this cannon, it's going to go around and around, and it's trying to fall to the Earth, and gravity's trying to pull it down. Oh, it gets back to where you are, and you need to duck so you don't get hit in the head. The idea is, if you go fast enough, you will go into orbit. And we refer to that as a constant state of free fall. Remember that free fall means an object is falling with only the force of gravity acting on it. So once we've fired our cannon, it's trying to fall towards the Earth. Gravity's pulling it down, but the faster it goes, the more range it has, and if I can make it go fast enough, it'll have such a big range that it's able to reach and go into orbit before it falls to the surface. Now, this velocity that we need to stay in orbit a certain distance from the center of the Earth is called orbital velocity. So we're going to come up with two equations on how to calculate that. Imagine this is the Earth, and the dotted line going around would be our orbit. The velocity is going to be tangent to the path, so if it's going around clockwise, this would be the direction of the velocity. And then the centripetal force is because it's moving in a circle and it's directed toward the center of the Earth. Other forces that are considered toward the center would be the weight of my orbit, or of my thing going around in orbit, and also that gravitational force from the universal law of gravitation that we talked about last time. So for this one, I'm going to set the centripetal force equal to the weight of my object. I'm going to make some substitutions. The centripetal force is equal to the mass times velocity squared over the radius, and then the weight of the object is equal to the mass times the acceleration due to gravity. Notice that the masses cancel out, and that leaves me with v squared over r is equal to the acceleration due to gravity. So because I'm moving around in a circle, this centripetal acceleration, the v squared over r, happens to have the same value as the acceleration due to gravity, which would be 9.8 meters per second squared on Earth. But I'm interested in how fast I need to be going, what this velocity is to stay in orbit. So I'm going to keep rearranging until I solve for v. So I'm going to multiply both sides by r. So that would be g times r. And once I take the square root of that, I get the orbital velocity as equal to the square root of little g, which for Earth is 9.8 meters per second squared, times r, which would be the radius of my orbital path. You can remember this as the square root of grrr, because sometimes physics makes you mad. Or, oh, there's the pirate version. Remember that it doesn't matter which order you multiply things, so you can think of this as the pirate formula because it's the square root of arg. Yes, I know I'm a dork, but I have to make your notes interesting somehow. For our second method, we're going to set the centripetal force equal to that gravitational force from Newton's universal law of gravitation. So let me do mv squared over r. And I'm going to go ahead and add a subscript of an O for my object that's in orbit. And then the universal law of gravitation was the big gravitational constant. There were two masses. One is going to be my object in orbit, and the other one is going to be the mass of the Earth. That's the thing I'm orbiting around. And remember, it was over d squared, but a radius is a type of distance, so I'm going to put r squared right here. We can reduce a couple of things. mass of the object cancels, one of those r's cancel, and we're left with v squared equals the gravitational constant times mass of the Earth over the radius of my orbit. Once you take the square root, you're going to have that gravitational constant times mass of the Earth over the radius of your orbit. And for us, we are doing mass of the Earth, but this mass can be any mass that you're orbiting around. So if I wanted the orbital velocity for one of Jupiter's moons, then I would use the mass of Jupiter because that's the thing being orbited. And remember, for both formulas, the r is the radius of your orbit. So let's do an example problem. You are given the radius of the Earth, and I'm going to say that the thing that's orbiting the Earth is not very far off the surface, so I'm just going to use the radius of the Earth as my orbital radius. You're given the mass of the Earth. You also know that little g is 9.8 meters per second squared, and the gravitational constant is 6.67 times 10 to the negative 11th Newton meter squared over kilogram squared. So pick one of the two formulas. You can either plug in and do the square root of little g times r, or you can try the gravitational constant times the mass of the Earth divided by the radius. So try each of these and see what answer you get for both of those. Using this first formula, you should have gotten a value of 7901 meters per second, and I just put that in scientific notation. And for the other version, you got 7906 meters per second. And again, I put it in scientific notation to show you that either formula would give you the same answer. So on your test, I would give you enough information for either of these two formulas, and you would have to be able to solve for the orbital velocity. I did write you a note to be careful of typing and using your parentheses, especially because we're working with such large numbers when you go to divide by the radius. So when you're doing your calculations in your calculator, just be careful of where you put your parentheses so that you get the correct exponent. If you need help with that, come in and I'll be happy to show you. At the beginning of the chapter, we talked about the period of an object as being the time it takes to make one full revolution. Well, the same thing applies to something in orbit. So the time for a planet to orbit once around the sun is called its period. The object does move a distance of 2 pi r during its period, so we are assuming a circular orbit, even though it might not be exactly a circle, but it's going to be close enough for our purposes. And I won't go through the derivation. It's not important for you guys, but you do need to recognize the formula for the period of something going around in orbit, and it's going to be equal to 2 pi times the square root of r is the radius of your orbit, and we're actually going to cube that, so you'll do the caret to the third on your calculator. And then we're going to divide by the product of the gravitational constant times the mass of the thing being orbited. Your units will still work out and you'll end up with seconds, just like any of the other periods that you've studied previously. So we have an example problem. We've got a satellite orbiting the Earth 225 kilometers above the surface. You're given the mass of the Earth and the radius of the Earth. We want to know the satellite's orbital speed and its period. Notice that we're given a large distance above the surface of the Earth, so we actually need to find an orbital radius. So we're going to add that distance to the radius of the Earth to get our total orbital radius. So let's do that first. Notice that I changed the kilometers to meters before adding. So now I have a new orbital radius, and we're asked to find the speed first. Since we're given the mass of the Earth, I'm going to use that second formula that we figured out. You could try the other method with the acceleration due to gravity and this new radius that we found and see if you come up with the same answer, but I'm going to use this formula and show you the steps. You should get a value of approximately 7,762 meters per second, and you're welcome to put that in scientific notation. It would be 7.76 times 10 to the third meters per second. Next, we're asked to find the satellite's period, so I'm going to switch screens and we'll work that one out together. Remember, your formula for the period of a satellite is 2 pi times the square root of r cubed divided by the product of the universal gravitation constant and the mass of the Earth. So let's plug in those numbers. So it should look like this. And remember, if you need help typing on your calculator, come in and I'll work with you on getting those parentheses in the correct spot, or show you how to break it down into smaller chunks and we can write out all the steps. But you should be able to calculate a period of 5.35 times 10 to the third seconds. Okay. If you wanted to change that into minutes, or if you were asked to do that conversion, that would be approximately 89 minutes, or almost an hour and a half. So remember, you might still need those time conversions if you're asked to find minutes or hours for a period. As always, don't forget to come in and ask for help if you're having difficulty with any of these example problems.